All right, so tell me you recognize what this looks like. Thank you. This is the business end of the bicycle, often called the drivetrain. I'm using this because I think most all of you, not all, but most all of you have a shared experience that you've probably learned to ride a bike. Now, it's not ubiquitous. There are some of you in the room who may never have. How many of you have ridden a bicycle successfully before? All right, so it is pretty common that this is kind of like, I always used to refer to it as that you have to get your kids all your shots. One of the shots they have to get is they have to learn how to ride a bike, So you have to teach them how to drive, ride a bike, eat with a fork, stuff like that. Just got to make sure that kids can do all these things. Well, here. I've watched some of you people in the lunchroom, and there are people who can eat with the fork correctly. Now, I bring up the bicycle for a number of reasons. Clearly, there's a whole rotational thing going on here. And it's hard to appreciate all the nuance, but a bicycle is a combination of wheels and axles, which at its heart is a simple machine. The other simple machines, like levers, we're going to talk about levers when we come back, and torque and stuff like that. And we've talked about pulleys as a means of redirecting force, but we haven't talked about any of them as a simple machine. The only simple machine we've actually talked about is an inclined plane. And as I say, simple machine, most of you don't appreciate, I think, the nuance, but a simple machine allows you to apply less force to do the same amount of work. So it helps you in lifting things or in moving things from one place to another. And you can also use it in the reverse. I zip-tied a kid's bag shut today. It was Joe's, yeah. So he had his backpack sitting there, and I had a zip tie sitting on my desk, and I felt like I should zip tie his bag together, because that's always fun. If you want a fun time, zip tie somebody's bag closed, they're not looking, and that way they're going to have no fun that day because they can't get into their bag. But I always keep a pair of wire cutters close in case somebody comes into my room, and this used to be a bigger thing, saying to me, "Mr. Sheldon, somebody zip tied my bag close." And I would laugh. We'd have a laugh. I'd make them pay me, and then I'd cut their bag open so they could get into it. Now, if you really want to enjoy this, you turn their bag inside out and zip tie it closed. Oh, yeah. That's so mean. They don't even get the straps anymore. What's that?
Isn't zip tie like the bag?
You don't know what a zip tie is? Sorry, dude. I used my only zip tie that was here. I have a whole bag of them in the stock room, but I'm not going to go get them right now. But keep your bag close. Because if you don't know what one is, you might need to discover. Anyways, in order to cut the zip tag off his bag, I used a pair of wire cutters. Now, they're not really wire cutters. They have another name, but these allow you to use leverage. It's a lever. I apply a small force on this end. I get a lot of force on that end. You don't want to get your finger caught in there. And mechanical advantage is the same word as simple machine, and it means the same idea. A bicycle is an example of how a wheel and axle can provide mechanical advantage. It's an exchange of force for distance. Now, how many of you who have ridden a bike have a bike that has gears in it, where you can select how difficult it is to pedal? Well, the number got a lot smaller, because some of you enjoyed riding bikes, and some of you thought, yes, I've done that, I don't have to do that anymore, and haven't ridden since it was, a tiny little bike. But some people do. I enjoy riding a bike. Mostly it's easier on my joints now that I'm old. So I ride to work when I'm not having to bring somebody here, because I can, and I need to make sure that, when you get old, you reach a point where you have to find time to exercise. You guys probably have a lot more available time for exercise. So I ride my bike to work. There are important functions here and important vocabulary I'd like you to know. For example, if you look closely at the bicycle mechanism, you'll recognize that if you move the pedal this way, this whole forward apparatus turns, right? You guys understand what I'm saying? It's important to understand that the pedal, the front sprocket, which is what it's called, or the front crank on your bike, it all moves with the same angular speed. And you might have 2 or 3 different things that are all connected together. My bicycle has 2 different gears on the front, and there's the pedal. Now, bless you. We all good? Yeah. All right. That was a solid sneeze. Somebody in my other class attempted to sneeze, and it didn't work for them. It was one of these. I hate that sneeze. No, it wasn't a COVID sneeze. It was just it was arrested development. Like he was developing a solid sneeze, and then at the last minute decided, I really don't want people to hear me sneeze, and so he held it in. How terrible is that for the poor sneeze? It's been working its way out of him all day. You have to set the tone. You have to set the tone. All right, back to work. So, the first part of this, the part that you are involved in, we say that these things in the front are coangular. They're coangular because they all move at the same angular speed. They have the same angular displacement. They have the same angular acceleration. All these things that are connected together. And this is where the energy is being placed into the system. So when we start talking about applying a force to the pedal and getting the pedal to turn in a circle, you are, in a sense, already using mechanical advantage in the first part of the bicycle. If you look closely, you're going in a much bigger circle, your pedal, and you're pulling on the chain, which is going in a smaller circle. As I said to you before, mechanical advantage is about an exchange. You're exchanging force for distance. So by your feet going through a larger distance, you apply less force than the force that's being applied to the chain. The chain is experiencing more force because it's being applied over a smaller distance. This is how a wheel and axle works. The coangular parts of a system are the simple machine part of a wheel and axle. Now, the chain provides 2 things for us. And if you've ever ridden or seen old bikes, like from the other turn of the century, 1900s, with the big wheel in the front and the little wheel in the back, they often had to pedal backwards to operate their bike because they didn't use a chain. They used a direct drive gear. We use a chain, and one of the reasons we use a chain is not only to distribute the force to the rear of the vehicle, the rear of the bike, but the other reason is to redistribute the direction. We want to have a gear in the back, but if these 2 wheels were touching, then this one would go in the opposite direction of this one. So the chain ensures that both wheels go in the same direction, so you have a natural feel that you are pedaling in the forward direction and the bike goes in the forward direction. Has anybody ever pedaled a bike that does the reverse, where you pedal backwards and the bike goes forwards? In the beginning, it's a bit of an unnerving experience until you get used to it. So obviously, the chain connects the outer edge of the forward sprocket, we'll call R1, and the rear sprocket, which we'll call R2. Now, this part's a little bit more challenging to understand. But the forward and rear sprocket, because they are connected by a chain, their outer edge is collinear. Now, collinear means that they have the same speed on the outer edge of the circle. They're connected by the chain, so whatever the speed of the chain is, whatever that velocity is, that's the speed of the outer edge of both the forward sprocket and the rear sprocket. Now, I want you to understand what that means. The front has an omega for the front times R1 in the front. Right? Because the radius in the front and the angular speed in the front combine together to give you the linear speed at the outer edge of the forward sprocket. Well, in the back, that has to be equal to the same ratio, but for the rear sprocket. This part is how gears work. And if you have a bike with gears, you understand that you can manipulate the radius of the forward or rear sprocket. And that ratio determines the ratio of how the rear wheel spins. I mean, if you look closely at this, and I want to look just at this for just a minute. I'm going to just do a little bit of cross multiplication. Let's put it right here so we have space. This is our ratio. Now, in this bike, R1 is bigger than R2. Pretty typical of most bikes. Which means if R1 is bigger than R2, W2 has to be bigger than W1. Which means the rear wheel spins faster than the front wheel. That's a gear ratio. And the bigger this number is, the bigger the difference in this speed is. This is another form of mechanical advantage, but it works in the opposite direction. Anybody who's ever ridden a bike knows that the higher the gear, the harder it is to pedal your bike. It's likely you would start in a lower gear, get up to a speed, and then advance to a higher gear. But this gear ratio is what really gives you the experience of increasing the speed of your bike much faster than you're moving your feet. Cyclists today, you see those groups of annoying cyclists on the side of the road getting their morning exercise in. They're pedaling an average of 20, 25 miles an hour on the road. Some of them hitting the peak of 30 miles an hour. They make me crazy. In their little tight little spandex suits, going super fast, super close to each other. But yeah, they can be going 30 miles an hour. What's that? The fastest I've ever been able to get is going downhill on the bridge on the trail. And even that, like 22, 23 miles an hour, that's terrifying. One little kid jumps in front of you with their stupid little parents and playing on the trail. You're gonna plow them over. Oh, makes me crazy. Now, of course, the rear of the bike, another set of mechanical advantage, right? The rear wheel is connected to the rear sprocket. And for this, we have yet another co-angular arrangement. So, taking a look at all the places where there's going to be mechanical advantage, one rotation of the pedals produces a huge rotation of the rear tire, many more rotations of the rear tire. And it's all about this arrangement of gears. Now, my expectation about your knowledge isn't that you could take a bicycle and break it down and talk about all the mechanical advantage. I want you to understand how ratioing of gears works. And I'll ask a question or two on the next test. The most likely question you'll see on a test will be something simple. Probably something more akin to this, where there are two wheels in contact. And you might be asked questions about the speed or the displacement between these two gears. This is pretty typical of what they ask. And they usually don't ask very much, but they'll ask just enough. Like they'll say, this is the drive wheel. And then they'll ask, they'll have like a kid's riding on the ride over here. So they might say the drive wheel reaches this speed. What is the speed of the ride? And then afterwards, they ask questions about the kid on the ride. So they'll have a starter question, which is to see if you understand that there is a ratio of gears here, just enough to get you started. And then they'll start asking questions about like centripetal motion or angular energy or something like that regarding the kid on the ride. Almost all of your amusement park rides, like at the state fair or in little carnivals, they have a drive wheel that is just set up to the side, and that's what causes your whole ride to spin. They don't drive them directly. They drive them using something like this, a small wheel on the side. So if that motor burns out, it's easy to replace. If you drive all these things directly at the middle, when those burn out, they're hard to replace. So you guys ever seen those rides like the Zipper? They have like a bunch of arms, like that. And then there's, some places for you guys to ride at the edge like that. And the whole thing spins, and then these guys spin. If you ever look closely at that, there's a little drive motor off to the side and a belt that turns that. That's way, if it breaks, they can replace the belt easy, they can replace the motor easy, but it's not all part of the whole assembly. And they do that for a number of reasons. One of them is safety, one of them is for maintenance, to make the maintenance on these rides easy. You've seen these guys who operate the carnivals. They got 3 fingers and 2 teeth, and they're the ones who maintain the safety of the equipment. So you'd want that to be easily done and easily accessible. So yesterday, we're going to combine this with what we talked about yesterday. I'll recall we talked about the idea of an object rolling down a ramp. You guys remember this? We did rolling up a ramp. I'd like to see how much of this kind of calcified for you. If I was to ask you to perform something tomorrow, it'd be a similar question to this. I said I might have you perform something for a little credit here at the end of the week. This is the problem I would give you tomorrow. So I'm going to give you a little bit of details here and see what you guys are capable of doing. Let's say we have let's go with a solid sphere. And it is, and I'm going to see how much you guys have been, paying attention. Solid sphere, mass M, and I'm going to give you a choice. For basic credit, I'll tell you that the edge of the ramp is a distance h above the ground. For advanced credit, I will tell you that this hill is length L and the incline makes an angle theta. And let's say that the sphere has radius r. I would like an expression for how fast the sphere is going when it's rolled to the end of the hill. You can assume that there's enough friction to get the sphere to roll without slipping. So I want V at the bottom of the ramp. Basic credit. You can have M, R, H, and G in your answer. If you want to have advanced credit, L, theta, R, M, G in your answer. Now, we did this problem yesterday. It's the reverse of the problem we did yesterday. The one we did yesterday, we started with the energy at the bottom and rolled it upwards. Today, we're starting at the top, rolling it downwards. So you have a model that you can base this on. Take a look at that model. But ultimately, if you can do this one, I will be happier. If you can do this one, it's adequate. Okay? But you need to look up solid sphere. That's from a couple days ago. Try it. So MGH at the top. Now, H over L equals sine theta. Right, I see a triangle there. Do you see a triangle there? H is the opposite side, L is the hypotenuse. So I could write H as L sine theta. I don't want you to get hung up on something like that. They could easily place it in terms of L and theta. Don't make that a problem. Do you see why I want to make sure you can be flexible here? H is important, but giving you H isn't necessary. Now, that being said, I see two kinds of energy at the bottom. Do you guys see that? All right. Now, kinetic energy is pretty straightforward. What we're trying to do is we're trying to get the rotational energy into similar terms as the kinetic energy so we can combine them. We want everything in terms of V. So you need to bring something to the table here to make this work. The first is we need the moment of inertia. This determines how much rotational inertia there is. And a sphere is 2/5 mr squared. But also, we would like it in linear velocity, not angular velocity. If it is rolling, then we are allowed to make this substitution too. So when I do both of those substitutions, that's what I get. R's cancel in this case, and I'm left with 1/2 mv squared plus the 2's cancel, so 1/5 mv squared. Common denominator of 10 gives me 7/10 mv squared. There's a subset of you, about 3, who probably don't add fractions together easily and don't know how I got that. Don't keep that a secret, but you probably don't want to share it in front of the room. Come get that fixed. The other side is still mgh, or mg L sine theta. Now, the m's will cancel here, so I have either 7/10 v squared equals gh, or 7/10 v squared equals gl sine theta. Thus, v is 10/7 gl sine theta, or v is 10/7 gh.